All right, so welcome back to the last aspect of the second week where we are going to actually see the whole Matroid framework at work with respect to one concrete problem, which is called scheduling with deadlines. So as I've been promising you, this is a problem that does have a valid greedy algorithm, but instead of coming up with the algorithm and proving that it's correct by hand, what we will do is we will come up with the algorithm, but we will argue that it's actually correct because it enjoys the matroid structure. And then the actual correctness is just going to be because of the theorem that we saw earlier this week, right? So that's the plan. And let me begin by introducing the problem to you. So what we are given is a collection of n tasks which are to be completed in n days. And each task requires your attention for one full day. So you cannot do 2 tasks in one day. And because you have to complete n tasks in n days, you cannot also skip days. So you have to basically do 1 task per day, right? What's interesting about the problem is that these tasks have deadlines. So there is, in some sense, a target by which you have to complete the task. And there's also a penalty if you can't finish the task within its given deadline. Okay, so you want to minimize your total penalty and you want to figure out in what order should you complete the tasks if you want to minimize your penalty. Okay, so let's say that we have an array D, which is the deadline array. So the ith entry in D gives you the day by which the ith task should be completed to avoid a penalty. And you also have a penalty array P, and P of I gives you the penalty that you have to pay if you fail to meet the deadline for the ith task. Okay, so the deadlines are numbers between 1 and n because they tell you by which day should the task be completed. The penalty values are, again, you can think of them as being non-negative rationals or reals, right? So the p values are just these numbers. Now, what is a schedule? A schedule is basically a permutation of the integers from 1 to n. And what does the schedule suggest? Well, it suggests an order in which you want to complete the tasks. So for instance, if n is 3 and your permutation is 2, 1, 3, that means that you want to finish the second task on the first day, the first task on the second day, and the third task on the third day. So I hope that makes sense. Now you can associate with each schedule a cost, right? So let's talk about the cost of a schedule. Well, what is the cost? It's going to be the total penalty that you pay if you follow this schedule. So let's write down what that's going to look like. So we go over all the tasks. We look at the penalty associated with the ith task. And we know that this penalty should be triggered only if you failed to meet the deadline. So let's look at when we decided to do this task. That is going to be pi of I. That's the day that we decided to do the ith task. And if this date happens to be greater than the deadline that was given to us for the ith task, that's when we are in trouble. So I'm going to use this notation to say that this value here is 1 if the statement is true, and 0 otherwise. So this is a pretty common notation that you may have come across in other contexts as well. So you write something like a statement inside square brackets, and this whole thing takes a value of 0 if the statement is false and a value of 1 if the statement is true. So that makes it convenient to write down expressions like this. So for all the tasks that you complete within the deadline, which is to say that this statement here is false, you manage to finish it within the deadline, this works out to 0. So then the penalty gets basically stifled. It's not going to show up in your expression. But if the statement is true, then this expression works out to 1 and the penalty gets added, right? So that's the cost of a particular schedule, right? I hope that makes sense. Maybe let's work through a small example just to get a feel for what's going on. So let's say that n is 4. So you have 4 tasks to complete in 4 days. Let me call these tasks A, B, C, and D. And let's say that the deadlines for the tasks are, you need to finish the task A within the second day, B within the first day, C within the first day, and D by the 4th day, right? So these are the deadlines. Notice that the deadlines don't really have to be a permutation. So in particular, you could have a demand which says that all the tasks should be finished by the first day, in which case you will have to pay a penalty for at least n-1 tasks, because there's only one task that you can do on the first day. Or you may have some very relaxed deadlines where all tasks have a deadline of n, which means it doesn't really matter because you're not going to get any penalties at all. So you can do the tasks in whatever order you wish, or it could be anything in between like we are seeing now. Okay, and so these are the deadlines, and let's look at the costs. So just to be consistent with the color scheme from before, let me change the deadlines so that they are in green, and now let's put down some penalties. So let's say the penalties are 10, 20, 30, and 40. Luckily, the task which has the most relaxed deadline has the highest penalty, but in this example, therefore, we don't have to worry about it. Let's look at a couple of different schedules and work out their cost. So let's say pi 1 is, we do it in the order in which we are given. So A, B, C, D. We do A on the first day, B on the second, C on the third, and D on the fourth. In this case, A incurs no penalty because it had a deadline of 2 and we managed to do it on the first day itself. But B and C are both going to trigger penalties because they were both supposed to be done by the first day, and we didn't manage to finish them within the first day. D is doing okay because it was supposed to be finished by the 4th day and we managed to do that. So the total cost associated with pi 1 here is going to be 20 plus 30, which is 50. Now, can we do better? Well, I think it's kind of clear that completing task A on the first day was probably not a good idea because we did have some breathing space for task A. So we might as well do it on the second day because we can still manage to not incur a penalty by doing it on the second day. So let's try saying that we'll do a different task on the first day. And which one should that be? Well, between B and C, and especially if you're thinking greedily, it's probably better to do C within time because C has the greater penalty associated with it. So let's try C first. And now we have a choice of B, A and D for the second day task. And notice that if we don't complete A on the second day, we are going to incur a penalty. Whereas for B, we have already incurred a penalty. So there is no point in rushing into B. The penalty is the same no matter how much you delay it. So it's a binary thing. You either finish it on time or you don't. If you don't finish it on time, it doesn't matter by how much you were delayed. The penalties don't increase linearly with the amount of delay. Although that may be a more realistic model, that's not what we are working with here. So notice that with B we are already sunk, so we might as well try to save our lives with A. So we finish A on the second day, and then it doesn't really matter how we complete B and D, because D has this very generous deadline, so you would not incur a penalty anyway, whether you do it on the third or the fourth day. So I'm just going to stick to this sort of an alphabetical schedule between B and D. So now let's look at what tasks we are okay with. So by finishing C on the first day, we actually are good on C. By finishing A on the second day, we are good with A as well. B is going to incur a penalty because we crossed over its deadline by a couple of days, and D is fine again because we finished it on the fourth day and it had a deadline of 4. So the cost of this schedule here is only the penalty associated with B, which is 20. And you can see that this is actually the best we can hope for, because B and C both have a shared deadline of the first day, and since you can do only one task on one day, you had to pay a penalty for either B or C. There is no way around it. And we have paid the lesser of those two penalties with this solution. So that's actually the best that we can hope for in this example. Now, if you think about it, the solution that we're looking for in this problem is actually a permutation and not a subset, unlike some of the other examples that we have seen before. Like a spanning tree is a subset of edges. In the class scheduling problem, we had to pick out a subset of classes and so on. But here, what we want is actually a permutation, so it has a slightly different flavor. And you might be wondering, where do matroids come in? Because when we are working with matroids, we are working with a family of subsets over a universe, whereas here the solution concept seems to be a permutation. So how do we relate the two? So it's not obvious, but what we are going to do is actually make that connection, because that's what I've been promising all along. So let's try to associate a family with this problem, a family of sets with this problem. So for any schedule, notice that we have a natural partition of the set of tasks into two parts, which is the late tasks versus the remaining tasks. We are going to call them on time. So if we just go back to this example for a bit, the highlighted tasks are the ones that are on time, and the underlined tasks are the ones that are late, right? So associated with every schedule, we have this sort of partition of the set of tasks. And notice that if two schedules give you the same partition, they have the same cost associated with it, even though the schedules themselves may have been different. So just as an example, let's think of pi 3 as being the following schedule. And notice that this has the exact same cost as pi 2 because we have the exact same task that is late, even though the schedule is actually different. So you would be executing the tasks in a slightly different order in pi 3 compared to pi 2. But notice that that's a distinction that we don't care about, because we are only interested in figuring out what the costs of the schedules are. So that gives us some hint about how we might be associating subsets with this problem. So notice that the key observation that I want to make here is that the cost of a schedule is completely determined by the subset of tasks that are completed on time. So this is going to be the key observation that allows us to think about this problem in terms of matroids and families of sets, even though the solutions are permutations. Okay, so in particular, let's say that a subset of tasks, which is really 1 to n. So let me maybe just say that. So we're going to say that a subset of tasks is realistic if there is a schedule where all tasks in X are on time. So that means that we can actually manage to complete all of the tasks that belong to X on time. The others I don't care. So if there is a schedule that achieves that, then X is called realistic. Okay, let's build up some intuition with some examples. For instance, from the tasks that we saw a while ago, we had A, B, C, and D, and we had deadlines that looked like 2, 1, 1, 4. So is the subset BC realistic? I think it's kind of clear that it's not, right? Because both of them have to be finished by the first day. So there is no way that we can complete both of them on time, right? So for the first day, there should be at most one task that has a demand of being completed by the first day. So in general, if you give me some collection of tasks, right, and I look at what are the deadlines that are associated with these tasks, if I have 2 tasks that are supposed to be completed by the first day, then that's not a realistic set. So there should be at most one task that has a demand of being completed by the first day. What about the number of tasks that have a deadline of 2? Well, once again, if we have more than 2 tasks that have a deadline of 2, then there is no way that this set is realistic, because when we look at these 3 tasks, within the first 2 days, we can only finish 2 of them, right? We cannot do more. So this is clearly unrealistic. So at a minimum or at a maximum, actually, we should only have at most 2 tasks that have a demand of being completed by the second day. In general, for any I between 1 and n, the number of tasks in X that have a deadline of I should be at most I. Because if you have I plus 1 tasks in X, which all have a deadline of I, notice that in the first I days, you can complete only I many tasks. So if you have I plus 1 tasks that have a demand of I or a deadline of I, then there's no way that you can meet all of those deadlines simultaneously. So this is a necessary condition for X to be realistic. It turns out that it's also sufficient, because on day 1, you have at most 1 task that has a requirement of being finished on day 1. So if you have exactly 1 task, then you finish that. If you have no tasks, then look at everything that has a deadline of 2. That's going to be at most 2 tasks. So again, if that's exactly 2 tasks, then you can schedule both of those. Otherwise, you always have enough room to accommodate the tasks that you need. So you can turn this into a proper argument, but hopefully the intuition is clear. If you have, of course, here, for instance, this set combined is again not realistic, because I think what I should be careful about is emphasizing that this is a deadline of at most I, because notice what's happening here. You have 2 tasks that have a deadline of 2 and 1 task that has a deadline of 1. So again, you're bottlenecked, because you will finish this task necessarily on the first day to stay on time. But now you have again a crunch situation for 2, right? So the number of tasks that have a deadline of I or less should be at most I. So I think that's something that I should have emphasized. This is not exactly I, but at most I. Okay, so hopefully it's clear that that's a necessary condition. If you violate this, then there is no way that you can actually manage everything. But if you don't violate this, then you can actually manage everything, because you can basically build up a schedule based on how the deadlines look. So essentially what you can show is that if you simply complete the tasks in increasing order of deadline, you will never get stuck and you will never incur a penalty. So just sort the tasks according to increasing deadline and keep completing them in that order. And because of the fact that the number of tasks you have to complete within the ith day is at most I for all I, you will essentially never overshoot a deadline. So that's why this is a necessary and sufficient condition for a collection of tasks to be realistic. So let me actually write this out so we have a chance to recap what we just said. All right, so this summarizes what we wanted to say, which is that a collection of tasks is realistic if and only if the number of tasks that have a deadline of t is at most t in this collection. So realistic sets are interesting for us because the larger the set of realistic tasks we can look at, the less the penalty we have to worry about, right? So if you can argue that the entire collection is realistic, then that's great because you can finish everything on time and there's no penalty. But essentially what you want is you want a realistic collection that has the maximum possible penalty, because the penalty is what you want to avoid, and everything that is in a realistic set is a task for which you don't have to pay a penalty, right? So you want to minimize the penalty of everything that does not belong to your set. So let's say this is our set of tasks, and here is a collection X of realistic tasks. So you want to find a collection of realistic tasks that has the largest possible penalty so that you minimize the penalty of all the tasks that don't belong to the realistic set. So I hope it's clear that minimizing the total penalty on a schedule is the same as saying, give me a collection of realistic tasks which has the largest total penalty, because then if I look at the schedule where I can finish everything in X on time, that's all the penalty that I don't have to pay, right? And so if there was a better schedule compared to what we have found, then if you look at all the tasks that were finished on time in that schedule, then you will see that that must have had a bigger penalty than what we have. So let me actually make that explicit. So I want to claim here that So what I mean here is that if you look at a collection of realistic tasks that maximizes the total penalty, and you look at the schedule associated with X, that is a schedule in which everything in X is finished on time, then that's actually the best schedule, okay? Or it's at least one of the best schedules. So suppose not, and suppose there was some other schedule pi prime that had a lower cost. So pi is the schedule where everything in X gets completed on time. Well, if the cost of pi prime is lower, right, that means let's look at all the tasks that were finished on time in pi prime. So this is the collection of all tasks here and here. And remember, the penalty that you pay is for everything that you did not finish on time. And because the total penalty is a fixed quantity, if the penalty of these tasks here is smaller, so let's say you have a penalty of P here and a penalty of Q here, and so if P is smaller than Q, that means that whatever the total penalty was, let's call that value T. So that total penalty here is T minus P, and that total penalty of the tasks that were completed on time here is T minus Q. So if P is less than Q, that means that T minus P is bigger than T minus Q, right? But then that contradicts our assumption that X actually maximized the total penalty of the completed tasks or the tasks that you finished on time, right? So hopefully this justifies the idea that what you're looking for is a collection of realistic tasks that has the maximum possible penalty. It may feel a bit counterintuitive because I've been saying that we want a schedule that minimizes the penalty, and now I'm saying look for things that maximize the penalty. But remember that these are the tasks that we are trying to actually finish on time. So this is the penalty that we don't pay, and that's why we're trying to maximize it. So it's a very natural sort of dual question that we have turned our problem into, and I hope that that makes sense and is not confusing. Okay, so now that we know what we are looking for as a subset, all that remains to be done is to say that the set of subsets that we are operating with actually forms a matroid. So in particular, this will be our final claim in this context. Notice that if we show this, then we are done because we have a family that's a matroid. We have a natural weight function, which is simply the penalties, and we are trying to basically maximize the penalty. We're looking for a basis. Once we show that this is a matroid, we are certainly looking for a basis which has the maximum weight, and we already know that greedy is going to find that for us. So essentially, this is the last thing that we have to prove to be done. Right, so let's first talk about the heredity property, right? So if you have a realistic set, that means you can finish all of these tasks on time. So there is a schedule that ensures that all of these tasks are getting completed on time. So now if you give me some subset of these tasks, well, I'll follow the same schedule. And since all of the tasks in X were getting completed on time, any subset of them is also getting completed on time. So heredity is easy to show. And we are done. The empty collection of tasks is vacuously realistic because there's nothing to be done. So that's not a problem either. So the only thing that remains to be shown is the exchange property. So once again, remember that what we are trying to say is that we have two sets, X and Y. They both belong to our family. In this case, that means they're both realistic sets of tasks. And X is bigger than Y, and I want to be able to pull in something from X minus Y, add it to Y, and still keep it realistic. Okay, so that's what we want to show next. And let's pause here for a second. If you want to give this a shot yourself, come up with some ideas, feel free to do that. This would be a good time. All right, so I hope you had a chance to think about this for a couple of minutes. Let's go ahead and actually show that the exchange property holds. So remember that X is the bigger set of tasks. We have X and Y. Both of them are subsets of realistic tasks. And what we want is to discover a task in X that can be added to Y while maintaining that Y is realistic. Now, not every task in X may be appendable to Y in this fashion, but all we want to argue is that we will be able to find at least one. So let me draw a timeline here, which is going to indicate the number of days from the start. So we have 0, 1, 2, and so on. And above and below this timeline, let me make a note of the number of tasks in X and Y that have a deadline of at most that particular day, right? So I'm going to put down these numbers x1, x2 and so on. And below I'm going to put down y1, y2 and so on. So notice that there must be some point of time where xt is going to be bigger than yt. So there exists some day t where xt is strictly bigger than yt. There might be multiple days when this is true, and we are going to move on this timeline from left to right, trying to capture the first time that this happens. Okay, why must there be some time when this must be true? Well, because it's certainly true at the end, right? Because when you reach the nth day, what is xn? That's just the total number of tasks in n, because every task has a deadline of at most n. And similarly, yn is the total number of tasks in y, because again every task in y also has a deadline of at most n. And by assumption, we know that xn is greater than yn. So this certainly happens at n, but it may also happen much earlier. So I want to focus on the first day, which is the earliest point of time when this inequality actually happens to come true. Okay, and at this point, because it's the first time that this has happened, I know that there must be a task in x which has a deadline of t specifically. So again, just to be clear, I am highlighting t as the earliest day on which xt is bigger than yt. Okay, so in fact, if it's easier to understand this with an example, let's actually run this through some numbers. So for example, what values can x1 take? Because x is a realistic set, we know that the number of tasks that have a deadline of day 1 is either 0 or 1, right? So let's say x1 has 0 tasks with a deadline of 1, and let's say y on the other hand perhaps has 1 task with a deadline of 1. Okay, this still maintains that both of them are realistic. Maybe x2 is 2. Okay, this is just an example, so don't take these numbers to heart. I'm just putting down a couple of arbitrary numbers to build some intuition. So maybe in x we have 2 tasks which have a deadline of day 2, and maybe in y we have 1 task with a deadline of day 1 and 1 task with a deadline of day 2. So the cumulative number in y is also 2, right? So far the yi's have been bigger than or equal to the corresponding xi's, right? Like I said, at some point this must actually flip in terms of the behavior of which number is bigger, because at the end we know that the xi's will catch up and in fact exceed the corresponding yi's. So let's just say that this already happens on day 3. So let's say that x2 has 3 tasks with a deadline of at most 3, but y has only 2 tasks with a deadline of at most 3, right? So x3 is 3, whereas y3 is 2. So that's our t. In this example, t is 3, right? And notice that this also means that there must be 1 task in x which has a deadline of 3, which does not belong to y, because so far y was either neck to neck or in fact bigger than x. So there must have been, because the flip happened on day 3 or in general on day t, it must have been that there was some task that got introduced then on that day with a deadline being of that day which does not belong to y. Because if every task with a deadline of exactly t that is there in x is also there in y, then x does not have this competitive advantage of xt being strictly bigger than yt, given that xt minus 1 is at most yt minus 1. And why do we know this about t minus 1? It's because we have pinpointed t as the smallest integer where this overtaking is happening, right? And I want to say that it's one of those tasks actually that I want to use for inclusion in the set y. Okay, so our first claim is that there exists a task in x with a deadline of t, where t is the smallest integer for which this inequality is true, right? Such that this task, let me label this task as Z here. So I want to claim that Z does not belong to Y. Right? And that is just like I said a moment ago, that is simply because of the way these inequalities behave, our choice of t being the smallest integer or the earliest day where the overtaking happens. So you must have found a task in X with a deadline of exactly t, which does not belong to Y. There may be multiple such tasks. Pick any one of them. The point is that there's at least one. Pick any one of them, and then our claim is that if you take Y and you add this Z to it, this is still going to be a realistic schedule or a realistic set of tasks. And why is this the case? Well, remember that a collection of tasks is realistic if and only if the number of tasks that you have in that set with a deadline of at most I for any I, the number of such tasks itself is at most I. This is what we want to prove here, right? So let's look at Y union Z. Well, how many tasks are there in Y union Z that have a deadline of t prime, where t prime is strictly less than t, right? So let's consider any of these days that show up before t. Well, Z does not even show up when we are considering days that are before t, because we know that the deadline of Z is t. So when we are considering tasks which have a deadline of t prime or earlier, with t prime itself being less than t, well, then those tasks are really a subset of Y itself. There's no Z business here. And that we know to be a realistic subset because Y was realistic to begin with. So that is easy. When t prime is less than t, we are really looking at a subset of Y. So those sets are realistic simply because Y is realistic. Now, what about the day t itself? On the day t, is it possible that in Y we have more than t tasks? Well, notice that yt was strictly less than xt. That's how we chose t in the first place. And because x is realistic, we know that xt is at most t because x is realistic, which means that since yt is strictly less than t, that's what we get by combining these inequalities. Yt is strictly less than t. That means that yt plus 1 is at most t, right? That means that you have that little bit of a buffer that you are getting by your choice of xt. So we have that yt plus 1 is at most t, and that is why this overall schedule, this overall set of tasks is also realistic. So everything works out finally. So this was the idea here. Of course, you could alternatively try to formulate a greedy algorithm explicitly and then claim that it works as far as scheduling with deadlines is concerned. And that would be the sort of thing that we were doing in week 1 for a variety of problems. But here the cool thing is that we basically viewed the problem as an optimization problem over a family that happens to enjoy the matroid structure. So we can basically outsource the effort involved in the proof of correctness to the proof that we have already seen for any matroid family on which a greedy algorithm is trying to find a maximum weight basis. So we are able to leverage this theorem that we saw last time and apply it to solve this problem. In the assignments, you will have more opportunities to explore ideas involving matroids. And of course, the story doesn't stop here, although we are going to be truncating our discussion of matroids at this point. But if you find the combinatorics or the mathematics of matroids interesting, then there are many fundamental theories in optimization that go back to interesting properties of matroids and its variants. And there will be some pointers in the course notes if you would like to pursue them further. So I hope you had a good time learning about matroids. Next week, we will take up dynamic programming, and that's going to be a whole new theme involving recursion, and efficient implementations. So I look forward to seeing you there and in the discussions around the assignments this week.